Welcome back, Night Owls. This is Dr. Nighttime, and tonight we're going over some generalizations of the product rule from calculus. Now, hopefully you remember the standard product rule. That derivative of f times g is f times g prime plus f prime times g, or the other way around, f prime times g plus f times g prime. And there are two particular generalizations I want to look at. First, what if there are more than two functions being multiplied, right? What if I have 3 or 4 or 5 functions all being multiplied and I have to differentiate all that? And the other is, what if we want a second derivative or a third derivative, etc.? So, more than two functions or higher order than just the first derivatives. So let's start with more than two functions. Let's consider the three function case. Suppose I have f of x times g of x times h of x, and I want to differentiate that. So that would tell me I'd have f prime x times the other two functions, right? G of x, h of x, plus f of x times the derivative of the product of the other two functions, g of x times h of x all prime. So this first term doesn't go anywhere. Then when I differentiate this product rule, right, I have f of x multiplied by g prime x times h plus g of x times h prime. Distributing, I get f prime gh plus fg prime h plus fgh prime. And I get that natural symmetry to it. I'm always multiplying the three functions, and I'm taking turns as to which one of them has the derivative on it. And the same thing works for more and more functions multiplied together. If I have 4 multiplied together, then I take the derivative. I get f prime ghi plus fg prime hi plus fgh prime I plus fgh I prime. So that's one of the ways of generalizing. That's the relatively easier one. Another generalization that's also useful is, what if I have to do more than just a first derivative? So if I know that if I have f of x times g of x and I prime that, right, differentiate that, I get f prime x times gx plus fx times g prime. Okay, fine. What if I wanted a second derivative? So, doing it the long way, I could just product rule each of these. Right? I have the sum of two products, so I differentiate, and I get two pairs of products. F double prime x times g of x plus f prime g prime plus another f prime g prime. The first f prime g prime comes from the second half of the product rule on this one, where I keep the f prime and differentiate the g. Then I do the first half of the product rule on the second part. I differentiate the f and keep the g prime. So both of them get me f prime g prime. And then I add an f g double prime. Now I combine my like terms. I get f double prime of x g of x plus 2 f prime x g prime x plus f of x g double prime x. What if I wanted a third order derivative? So I just differentiate. I now have 3 terms, so I need to do 3 different product rules one at a time. Doing this one, I get f triple prime x g of x plus this times derivative of this, f double prime times g prime, plus twice, I differentiate this one, f double prime g prime, so twice f double prime g prime, plus I keep this and differentiate this, 2 f prime g double prime. Next I move to the third one. Differentiate this one, f prime g double prime, and then do it the other way, f of x g triple prime x. I combine my like terms. I have an f double prime g prime and 2 f double prime g primes here. I have have 2 f prime g double primes here and 1 f prime g double prime here. So I get f of x g of x triple prime equals f triple prime x g of x plus 3 f double prime x g prime x plus 3 f prime x g double prime x plus f of x g triple prime x. 1, and so coefficients are 1, 3, 3, 1. This hopefully reminds you a bit of binomial expansion, where the coefficients form the rows of Pascal's triangle, and if I had, say, x plus a to the third power, it would be x cubed plus 3x squared a plus 3xa squared plus a cubed. Here, instead of powers of the two things, I'm looking at derivatives of the two components. So it's 1 f triple prime g plus 3 f double prime g prime plus 3 f single prime g double prime plus 1 f g triple prime. And I can do that for however many rows I need. And I'd like to show two examples of where this comes up. One of them actually comes from differential equations. If we have a forced vibration system, consider the forced vibration system y double prime t plus 4yt equals t cosine t. And I want a particular solution. If I were going to go through all this fully in the differential equations version, I'd find the solution to the corresponding homogeneous case, add a particular solution to this problem, and then get the full general solution to that differential equation. I'm just focusing on the particular solution. I'm just trying to find one function that satisfies this. And using the method of undetermined coefficients, we know to assume that y has the form at cosine t plus bt sine t plus c cosine t plus d sine t. And that's our initial guess. Since I have a y and a y double prime and no y prime, I probably wouldn't want to differentiate y first, and then differentiate that derivative to get a second derivative. I'd probably want to use second derivative product rule. So that's what I do. I look at the at cosine t. First thing I do is I take two derivatives of at. That goes to 0. That multiplies by something. It's 0. We ignore it. Then I have 2 times derivative of at, 2a, times derivative of cosine, negative sine, negative 2a sine t. Then I add at times second derivative of cosine t. Second derivative of cosine t is negative cosine t. So I have minus at cosine t. Now I do the analogous thing for bt sine t. Second derivative of bt is just 0, just like before. Then I have 2 times derivative of bt, so 2b, times derivative of sine, cosine, 2b cosine. Then I take bt on its own and multiply by second derivative of sine t. That's negative sine t, so minus bt sine t. And then the c cosine and d sine, second derivative of sine and cosine are just negatives of themselves, so I have minus c cosine t minus d sine t. I then add in second derivative of y plus 4 times the original. So this algebra happens. I have a negative at cosine t plus 4, because 4y, 4 at cosine t. Okay. I have negative bt sine t plus 4 bt sine t. Here they are. For the isolated sine and cosines without the t out front, I have a 2b minus c plus a 4c from here, multiplying y by 4. And for sine t, I have a minus 2a minus a d and plus 4d from here. Crunching everything in, I have to match my corresponding term. So since I have a 1t cosine t here, and I have all this stuff in front of t cosine t here, I know negative a plus 4a must equal 1, so 3a equals 1. Looking at the t sine t, I similarly get 3b equals 0, because there's 0 t sine t. So 3b equals 0, b must be 0. I looked at the isolated cosine term, 2b plus 3c times cosine t. Well, there's no isolated cosine t. There's a t cosine t, but we already accounted for that. So 2b plus 3c equals 0. This should be a plus, but it doesn't matter, because since b is 0, c has to be 0. And lastly, negative 2a plus 3d equals 0. We know that 3a equals 1. So a equals a third. D must equal 2/9. So I get y equals 1/3 t cosine t plus 2/9 sine t. And if you double check, if you take the second derivative of this function and add that to 4 times the original, you will get 1t cosine t and nothing else. Another question that I had a student ask me about recently. A student was going through some challenge problems and asked, what's the 35th derivative of x sine x? Now, it's rather unusual to make students take a 35th derivative by hand unless there's some sort of trick, which fortunately there is. I know the 35th derivative of this function is going to be x times 35th derivative of sine x plus 35 choose 1 times derivative of x, 1 times 34th derivative of sine x, plus all the other terms are going to be multiplied by second order or higher derivatives of x, which are just zeros. I calculate 35th derivative of sine x, it's going to be negative cosine x. So I get negative x cosine x. I have 35 times 34th derivative of sine x, it's going to be negative sine x. So I get negative x cosine x minus 35 sine x. And there's probably the only time there's an easy way to take a 35th derivative of a product of two functions. As always, I hope you found this useful and informative. And if you like the way I explain things and want to arrange private lessons, click the link in the description below. And until next time, this is Dr. Nighttime wishing you a good night.